right? Some more properties. If A is a diagonal matrix, adjoint A will be a diagonal matrix. Adjoint A will be a diagonal matrix. Hey, one thing. If A is a diagonal matrix, that is, say, D1, D2, Dn, and all other entries are 0. All other entries are zeros, etc. It's a diagonal matrix. Then, only for the diagonal elements you will have non-zero cofactors, right? Only for diagonal elements you will have non-zero cofactors, yes or no? For all other elements the cofactor will be 0 because it will get multiplied with 0, right? That means the matrix of cofactors will also be a diagonal matrix. The matrix of cofactors will also be a diagonal matrix, yes or no? No? I'm saying if A is a diagonal matrix, what will be the cofactor of this element? Because it will get multiplied. What's the cofactor of this? 0, 0, 0, 0, 0, 0, 0, 0. So except for the diagonal elements, cofactor of all other elements will be 0. That means the matrix of cofactors will have, except for the diagonal, all other entries equal to 0. Yes or no? That means the matrix of cofactors will be a diagonal matrix. Right? Right? So matrix of cofactors will be F, which is a diagonal matrix. Now, if you have a diagonal matrix and you transpose that matrix, it will still be a diagonal matrix. Because when you transpose this diagonal matrix, then realize that these entries will remain intact. And all other entries will get transposed. That means all other entries will remain 0 except for the diagonal entry. So F is a diagonal matrix, matrix of cofactors, then its transpose will also be a diagonal matrix. Right? So F transpose is also diagonal. F transpose is also diagonal. Yes or no? But F transpose is what? Adjoint. That means adjoint A is a diagonal matrix. F transpose is adjoint A, which is a diagonal matrix. Do you all understand this? Now, so that's this one. Let's look at next property. Adjoint of adjoint A is determinant A to power n minus 2 to the matrix A. This is a scalar. Determinant A is a scalar, k. K, A to power n minus 2, k to power n minus 2. Determinant A is a scalar. Now, adjoint A. Again, we start with A adjoint A equals determinant A, which is a scalar, into an identity matrix of the same order as A. Right? Now, I want to bring about adjoint of adjoint A. Replace A by adjoint A in this identity. In this identity, replace A by adjoint A. You know what I'm saying? Replace A by adjoint A in this identity. Clear? So when I replace A by adjoint A, so replacing this A by adjoint A, so this is adjoint A into adjoint of adjoint A is determinant of adjoint A, determinant of adjoint A into IN. Yes or no? Hello? We'll wait for your turn. Now, adjoint A is what? Matrix of cofactors transposed. Right? Is matrix of cofactors transposed. That's adjoint A, IN. But determinant of F transpose is the same as determinant F. Right? is the same as determinant f in. And did I not establish the determinant of cofactors would be determinant of a to power what? N minus 1. Did I not tell you this in the last class? Determinant of cofactors of a matrix would be determinant of that matrix to power n minus 1, where n is the order of that matrix. Refer to yesterday's class, right? So determinant of cofactors would be determinant of a to power n minus 1 into in. This is a scalar. This is a scalar, right? So we have in all adjoint a into adjoint of adjoint a is equal to this. Clear? Now, I need to get rid of this. What I do is, this matrix is equal to this matrix. I pre-multiply this with A because I have knowledge of A adjoint A. I pre-multiply this with A. You can pre-multiply and post-multiply in a linear algebraic equation, right? In a matrix equation, you can pre-multiply and post-multiply. I mean, if this is equal to this, then A times this will be equal to A times this. Or, if this is equal to this times A will be equal to this times A. That's post-multiply. Pre-multiply or post-multiply. Right? But A adjoint A I know. Determinant A to power, determinant A in. Is determinant A in? Yes or no? A adjoint A is determinant A in. So this is like determinant A in. Determinant A is a scalar. Adjoint of adjoint A. Right? A adjoint A is determinant A in. Adjoint of adjoint A equals, now this is a scalar, and the scalar has thoroughfare in an equation. It can come out, the scalar can come out or go in, right? So this scalar comes out, determinant A to power n minus 1 is a scalar, A times in, yes or no? Now, in times a matrix will be that matrix, isn't it? If in is multiplied with this matrix, then the outcome will be this matrix itself. Yes or no? In into this matrix will be this matrix. So in into this matrix is this matrix. Yes or no? And in identity matrix into a matrix is that matrix, isn't it? In into a matrix would be that matrix, isn't it? So in into this will be this. Have I confused you? Confused, huh? In into P. What is it? P, isn't it? So in into, say, P will be P, isn't it? Or P into in, that will also be P. Right? So I get rid of this. I didn't need it anyways. And A times in will be A. That's why it's called an identity matrix. Right? A times in will be A. So let me get rid of this also. Yes or no? All's good? Now, this is a scalar. I can divide throughout by a scalar. I'm not dividing by a matrix. So I can divide throughout by determinant A. But provided A is non-singular. Its determinant is not 0. That's when I can divide by determinant A. Determinant A should not be 0. A should be non-singular. Right? So if A is non-singular, I divide by determinant A. This will become to power n minus 2. What do you say? How about it? No? Am I buying curse from you? No? No, you're not cursing me? Adjoint of adjoint A is determinant A to power n minus 2 into the matrix A. would do good to remember this also, right? When you can remember so many uh, results in trigonometry, you know, beginning of class 11, this is all right. Huh? Yeah, yeah. Hmm? Ayush. Oh my God. Miss him, yaar. We had a galata of a time. So much of entertainment, unadulterated fun in my South Kolkata batch when he was around. So, huh? The point is, he did nothing. He always remained electrocuted. His presence was electric. Yes. He said, he used to tell me, he couldn't focus on academics too much because the quality of electricity in his house was not very good. So then, you know, I was taken aback. I said, now come on, would you describe what you mean by quality of electricity? I mean, 1 ampere of current here and 1 ampere of current there. How do you distinguish between the qualities of the two 1 ampere currents in different locations? But then, you know, he gave us enough ammunition to have fun at his expense all the time. All right, so this brings us to result 5. Adjoint of adjoint A is determinant A to power n minus 2 A. Obviously, all of this provided A is non-singular. A is non-singular. Good, right? Now let's look at this result. Essentially then, it's an outcome of this result. Let me take determinant of both sides in result 5. Let me take determinant of both sides in result 5. All right. So if I take determinant of both sides in result 5, then determinant of adjoint A is determinant A to power n minus 2 into the matrix A. Yes or no? If this matrix is equal to this matrix, then the determinant of this matrix must be equal to the determinant of this matrix. Right? Now, hey, did I tell you? Determinant of K is a scalar, times A is going to be K to power n times determinant A. Yes or no? Because every entry of A is multiplied by K. So you could have taken K common from each of the n rows and it would have become K to power n. Right? Now, my K is this. This is my K. This is my K. So determinant of K times A would be K to power n times determinant A. So that's going to be K to power n, means n into n minus 2. K is determinant A to power n minus 2. Whole to power n would be this into determinant A. Determinant of K times A would be K to power n times determinant A. Yes or no? Now this is like determinant A to power n square minus 2n plus 1. Yes or no? So this is like determinant A to power n minus 1 whole square, which is what we said. How about it? So this is this result. No confusion, right?